Hello everyone and welcome back. So today we are going to discuss about refraction. Okay, so yeah, let us go straight to the definition first. We know refraction pretty well. See, refraction is nothing but bending of light rays when it passes from one medium to another with different optical densities. Now here the term optical density is very much important and let us discuss it in detail. See, optically dense means what? Let us take two examples. Now you are seeing this slide, okay? In front of you, in the left hand side, there is a picture where light ray is incident, is going from rarer medium to the denser medium. Now, in this particular case, you can see that the light ray should follow the dotted line. Just let me clarify it once again for you. This light ray should follow this dotted line. But due to the denser medium, it is now following this line. So, why this is happening? See, optically denser means what? This medium, this denser medium is closely packed with so much of molecules, right? Now, when the light ray is going from this medium to that medium, this light ray has to face many obstacles, many resistance, and those particles is tend to bend this light ray towards the normal. Okay, and that is why this light ray is bending towards the normal, bending towards the normal. This is happen when light ray is traveling from rarer to denser medium. Okay, hope you understand this one. And in the next thing, that is when light ray is traveling from denser medium to rarer medium. So in rarer medium, there are less particles, less number of particles, and there are less obstacle. So light ray will go away from the normal. Of course, if there is no medium, no boundaries, then of course the light ray will follow the dotted line. But here there is two different medium. So of course the light ray will go away from the normal. It will bend away from the normal. So why this is happening? Because of the density of the medium, and this is called optical density. Hope you understand this thing. Now let us move straight to the main term associated with optical density. The term related to optical density is refractive index. What is refractive index? It is basically the ratio of velocity of light in vacuum to its velocity in specified medium. Meaning what? Refractive index is basically the, see, here it is. We can see that suppose here the velocity of light is v1 and here the velocity of light is v2. Okay, then the refractive index will be the ratio of these two velocities. Okay, the ratio of these two velocities. Now there are some factors, there are some facts which you have to understand about refractive index. So let us go straight to the fact number 1. See, if you have to know the definition of C, I think you know, that is C is nothing but, here I have written the velocity of light in vacuum. And what is V? Velocity of light in any other specified medium. Now, velocity of light is what? 3 into 10 to the power 8. Right? If I am not considering the relativistic approach, then this term C will always dominate over V. Okay? Because none of the particle could travel faster than C. So, of course, the ratio will be always greater than 1 because C always greater than V. So, refractive index could never be less than 1. Also, refractive index, this type of refractive index, that is n equals to C by V, this could be also referred to as the absolute refractive index. And the thing is there is a question, you can see. So I am not reading out the question for you. You have to read out the question and answer in the comment box. Okay. Next, laws of reflection. So there are two laws of refraction. So first one is the same as reflection. I'm not going to that, but the second one, which is the very important one and new to you. Second law states that the ratio of sine of angle of incidence to the sine of angle of refraction is constant. What is this? Let me clear it once again for you. See this picture. This is not clear, sorry for that, but I don't have more clear picture rather than this. Okay, so see, from the very basic source O, all the light rays from here, all the light rays are going from water medium to air medium. Air is the rarer medium here and water is denser, right? So we can see that incident ray is going in this direction and this is our refraction. Now see, here the angles are important here. So I1 and R1, just note this one carefully. Now for second ray, this is ray number 1, this is ray number 2, this is ray number 3. For ray number 2, now I have increases I1, means I2. I have increases the angle of incidence. Means here I1 is, okay, so it will follow this relation. So here the basic thing you can notice that as I am increasing I2, R2 is also increasing. Here I am increasing I3, R3 is also increasing, right? So here you can notice that which fact is remain constant here. The ratio is remain constant here. Now from this particular figure you can write in this way that angle of incidence, sine of angle of incidence divided by sine of angle of refraction will be equal to constant, and this constant is also known as refractive index. Okay, this refractive index, now you have another formula for refractive index, another expression for refractive index. So Snell's law, this thing is called Snell's law, this relation is called Snell's law. Hope you understand. Next we will go through a very special, a very important thing in class 12 concept, that is total internal reflection. See, I have taken here few examples. Okay, see it very carefully. Ray number 1, I am not considering this ray, starting from this one. Ray number 1. For the similar thing I will do. This is angle of incidence, angle of refraction. Suppose this is theta 1 and I am taking this as phi 1. Again I have increases theta 2. Okay, so this will become phi 2. Okay, so angle of incidence increasing, angle of refraction is also increasing. At a certain point when you are increasing all the things together, you can see that in the first case this is happening. Okay, in the second case you have increases in such a way that it touches the reference line and the angle of refraction becomes 90 degree. At this particular case you have to call the angle of incidence as critical angle. Okay, beyond that, what happen if we further increase? What happen if we further increase the incident angle and we make it more than critical angle? More than critical angle. What will happen? So this angle I is more than critical angle. Then there will be no refraction, although there is two medium present, but there will be no refraction. There is complete reflection, and that is why this is called total internal reflection. Okay, again I am revising it for you. What is happening here? I am increasing the angle of incidence and angle of refraction is also increasing. So I am just trying to increasing it in a regular interval. And what happened after some time? It attained the critical angle at which the angle of refraction becomes 90 degree. What happened if we further increase beyond the critical angle? Then there will be no refraction, there will be total internal reflection. Means the total ray will reflected back in the first medium itself. Okay, so first we will take the definition of critical angle, and then we will take the condition at which total internal reflection happens. So here is another picture. I have said it, but I think you have cleared the concept. Critical angle. Okay, this is basic, but I'm going to giving you a different definition. See, I can say in this way, at which angle of incidence the angle of refraction becomes 90 degree is called the critical angle. This is the simplest one. Also you can follow this, which is written here. Okay, now condition for total internal reflection. To follow total internal reflection, you have to understand this 2 points. We have to choose 2 specific mediums, and for a specific light only total internal reflection happens. And another point is there, the angle of incidence must be greater than critical angle, of course, otherwise total internal reflection will not occur. There is most popular mirage formation, which is the real life example of total internal reflection, and this is very unique one. Let me discuss it. Okay, see here, suppose here is my sun, cute one, and light rays coming straight to the eye of this human. Okay, now see, this is your sand, which is highly heated, desert and its formation, right? So the layer which is attached to it, the first one, will have more temperature, more heat. Next one will be a bit lesser heat. Next one will be a bit lesser temperature. Then next one a bit more lesser temperature. And if you go in this direction, the temperature will become will be decreasing, right? So what I'm trying to say here, that these layers is having different temperature values. As they are having different temperature, they should have follow different densities. Now, if they are having different densities, they are having different mu or different refractive index, right? Now, while the light ray is passing from different layer, it should have face a refraction. So, it will follow in this direction, right? It will come in this direction. Now, at particular angle, it will achieve the critical angle, right? And after that, after achieving critical angle, what will happen? If it further goes, it will suffer a total internal reflection, and it will go back to the previous medium. Hope this is clear to you. Now the light ray will follow this path, but human cannot see in this direction, in curved line they cannot see, so they will follow this path only. And here he can see a shaky image of this tree, and an illusion of water will happen, and this is called formation of mirage. So this is happening because of the total internal reflection. Hope you understand this thing. Again, we will take another example, and before going to that, I want to say one thing. You can really do this experiment at home, and you will be thrilled about that. Just you need to take these things, a glass, anything, a glass, a plastic bottle which is transparent, okay, and you need to take a laser light. Whichever color you are having, whichever monochromatic color you are having, you can take this, and you can see this picture suggests refraction, clearly a bending, you can notice, right? Interesting one. And here you can see total internal reflection. Must be this angle is more than the critical angle, so it suffers. It is actually going straight back to the first medium, right? Okay, so these two experiments you can perform at home easily. After that, let us have our last slide, and this will be your homework question. I am giving some hint as picture. First is, What do you mean by brightness of a diamond? Is it because of total internal reflection? If so, now if I'm changing the shape of diamond regularly, does it affect in brightness? I have given some hint as picture and also have drawn the ray diagrams for it. I am sure you can do it. And lastly, thanks for watching. Wait for our next video. Bye bye.